Welcome to Gradient Daily, where every single day we take a deep dive into an exciting AI research paper. I'm absolutely thrilled you're here with us. Today, we are looking at an explainer on something that honestly feels like pure magic. The paper is titled Lift4D, From the Illusion of Perception to the Reality of Computation. It's authored by Johanathan Littman alongside a frankly incredible team of researchers out of Carnegie Mellon University. Now, to set the stage for why this is such a big deal, I want you to imagine a magic trick. Imagine taking a standard, flat, 2D recording, just a casual video captured on your everyday smartphone, and instantly pulling the subject out of the screen, transforming it into a fully manipulable, true 4D object. You can spin it around, you can look behind it, and you can watch it move and deform through time as if you were walking around the actual physical thing. We're talking about a massive leap forward for the real-world creation of digital assets, gaming environments, virtual reality, and high-end movie production. And what's really going to be our focus today is the visual style that this system achieves. Previous attempts at this have looked glitchy, tearing at the seams, but Lift4D creates a visual style that is astonishingly coherent. So let's dive deep into exactly how the brilliant minds at CMU actually pulled this off.
To really understand the magnitude of the problem Lift4D solves, we have to talk about human perception versus machine perception. Think about a sequence of a rhinoceros walking behind a large tree trunk. For you and me, our human perception handles this with zero effort. We intuitively understand that a rhino is a 3D creature. Even when its midsection is completely blocked from our view by the bark of that tree, our brains seamlessly maintain object permanence. We know the rest of the rhino still exists, right? And we effortlessly track its shape bending and deforming as it walks. But for an artificial intelligence model, this exact same scenario presents an absolutely massive computational hurdle. It's a fundamental ambiguity. Computers are looking at what we call monocular, in-the-wild video. To an AI, that video is literally just a flat, two-dimensional grid of changing pixel colors captured from a single camera lens. The AI doesn't inherently know that depth exists in that scene, let alone full 360-degree geometry. So when the rhino goes behind the tree, previous AI models completely break down. They'll often leave gaping, jagged holes or horribly distorted geometry where the tree blocked the view, totally ruining the visual style of the asset. Lift4D, however, is doing something unprecedented. It recovers the full geometry, the exact appearance, and the complex deformation, including beautifully reconstructing regions that the camera lens never even observed.
Okay, here is our roadmap for today's explainer. We'll start by defining the core 4D reconstruction problem. Then, we'll introduce the Lift4D solution. From there, we'll break down connecting frames across time, sculpting deformable 3D objects, handling those tricky, unseen, occluded regions, and finally, we'll wrap up with the results and future implications.
Section 1. The 4D reconstruction problem. Let's unpack why this is so incredibly hard for AI. To truly appreciate why artificial intelligence struggles so much here, we have to look closely at the unconstrained nature of our source material, which is monocular video. This is video captured from just a single viewpoint or camera lens. There is absolutely zero built-in 3D depth information. We aren't using expensive LiDAR scanners, and we aren't using stereoscopic dual lenses. It's just flat RGB pixels changing over time. And the objects we want to capture out in the real world can be literally anything: a wild rhino, a flying bird, or just a person taking off a shirt. These objects undergo massive, non-rigid deformations, meaning they squish, bend, and stretch, and they suffer from severe occlusions, where parts of them get blocked. Now, prior approaches to solving this basically fall into two distinct buckets, and honestly, both have critical flaws that ruin their output's visual style. The first bucket uses feed-forward models. These try to directly predict a 4D output from the visual input in one single massive pass, but they are completely bottlenecked by the scarcity of true 4D training data. Because there isn't enough real-world 4D data to train on, they either rely on really narrow, category-specific templates, like a pre-built skeleton of a dog, or they train on highly synthetic, video game-like assets that simply do not generalize to the messy, unpredictable real world. The second bucket includes optimization-based methods. These use 3D priors just for the initial setup of the first frame, but then they rely solely on the flat video supervision for the rest of the sequence. Because they fundamentally lack temporal correspondence, meaning they don't explicitly track how the object structure connects from one second to the next, they degrade severely when the object moves aggressively or changes viewpoints. When a single lens camera fails to capture the geometry of what happened in a blind spot, these prior AI models are left completely guessing, resulting in a fractured, messy output.
So, before we look at how to fix this, we need to understand what mathematical format we are actually using to hold this complex 3D data. Enter 3D Gaussian Splatting. If you've been following AI graphics, you know this is a huge deal.
Think of 3D Gaussians as a highly efficient, explicitly manipulable visual representation of space. Instead of using a traditional wireframe mesh, it's a technique that represents scenes as millions of tiny mathematical blobs or splats. Each individual splat has a very precise 3D position in space, a covariance matrix that determines its stretched or squished shape, an opacity value, and complex spherical harmonics that represent its color depending on exactly what angle you're viewing it from. I want you to think of 3D Gaussian splatting like highly advanced, glowing digital clay. It's fantastic for capturing incredibly photorealistic visual styles. However, here is the catch. While existing 4D methods try to shape this digital clay over time, they often end up completely tearing or distorting it when the object undergoes large, non-rigid motion. The individual Gaussians basically lose track of their neighbors. This leads to a fragmented, glitchy mess when you render the object from novel views that the camera didn't see. The visual style breaks down because the digital clay essentially crumbles under the stress of movement.
Section 2. Introducing the Lift4D solution, a 3-pillar pipeline.
So how do we stop the digital clay from crumbling? Lift4D is a groundbreaking test time optimization framework designed to bypass the limitations of previous models entirely. The true elegant genius here is that Lift4D does not need massive, diverse 4D training data, nor does it require narrow, category-specific templates. It doesn't need to be told it's looking at a horse or a human. It is completely category agnostic. It achieves this remarkable feat by entirely decoupling the generative priors. Let me explain that. Instead of trying to train one massive, monolithic model that magically understands all 4D motion, which is incredibly hard, it uses highly capable, already existing 2D and 3D priors, routing each one to a very specific, specialized role in a curriculum-based test time optimization. It strictly separates the problem of getting the 3D geometry right from the problem of getting the visual style and appearance right. When we look at this architecture, it operates on a very clear 3-pillar pipeline. Pillar 1 is causal single-view reconstruction. This is where the system generates a coarse but temporally consistent geometric signal frame by frame. Pillar 2 is deformable 3D optimization. This takes those independent frames and distills them into a single, unified canonical 3D object that elegantly bends and deforms over time. And finally, Pillar 3 is the application of image priors for unobserved regions. This is the ultimate appearance phase, utilizing view-conditioned image diffusion to literally paint hyper-realistic textures onto the surfaces the camera never even saw, guaranteeing a flawless visual style.
Section 3. Connecting frames across time. Let's look at causal latent conditioning.
Let's dive deep into Pillar 1. If you were to just use an off-the-shelf single-view 3D model, like SAM3D, on a standard video, it will try to reconstruct every single frame completely independently of the others. The massive problem there is, if you string those independent 3D frames together to make a video, they flicker, they glitch, and they morph wildly. The geometry is completely inconsistent because the model is essentially suffering from amnesia. It's starting from scratch every single frame. To fix this catastrophic jitter, the CMU researchers adapted an existing image-to-3D model without having to retrain the whole thing from the ground up. They did this by forcing the underlying math to actually respect the flow of time. They achieved this through a brilliant process they call causal latent propagation. I like to think of this as passing notes across time. Here's how it works at a PhD level. The off-the-shelf model relies on rectified conditional flow matching. This means it denoises a structured latent representation, which holds the geometry, starting from pure random static noise. The major breakthrough here is that for the next frame in the video, instead of starting from fresh, independent static noise, they warm start the process. They mathematically blend fresh noise with the clean, already denoised structural data from the previous frame. By injecting the previous frame's clean structure directly into the starting noise of the current frame, the model is mathematically forced to generate geometry that is causally consistent. It firmly anchors the current frame to the past. This entirely prevents the geometry from wildly hallucinating frame to frame, laying down a rock-solid foundation for a smooth visual style.
Section 4. Sculpting deformable 3D objects using the canonical model.
Okay, so now that we have temporally consistent per-frame 3D reconstructions, we run into a new, complex problem. We essentially have a bucket of independent 3D meshes, one for every single frame of the video, but there is no overarching correspondence between them. They are separate, disconnected entities. Lift4D solves this by taking all these per-frame reconstructions and distilling them into a single master framework called a deformable canonical representation. This means one master set of 3D Gaussians is created to mathematically explain the entire video sequence through a highly advanced learned deformation field. This process of digital sculpting relies on initializing what are called sparse control nodes. I want you to think of these control nodes like the joints in an invisible skeleton, placed strategically all along the surface of our master canonical 3D Gaussians.
A neural network then predicts exactly how these specific control nodes transform in space and time across the video. By using a rendering technique known as linear blend skinning, these sparse control nodes elegantly bend, pull, and stretch the millions of tiny Gaussians fluidly. And the researchers supervise this complex alignment using a strict combination of physical positioning constraints and multi-view rendering consistency. Because it's a sparse parameterization, meaning the heavy math relies on just those key control nodes rather than calculating every single Gaussian individually, the computational cost is completely decoupled from the millions of underlying blobs. This is crucial because it allows for massive, highly complex, non-rigid motions without completely overwhelming the computer's memory, all while preserving the integrity of that Gaussian clay.
Section 5. Handling unseen occluded regions. This is where the real magic trick happens.
Now we hit the hardest problem in monocular video. If you are recording a video of a person taking off a jacket, their moving arms will temporarily block the camera's view of their chest. In an unconstrained, real-world video, if you optimize your 3D Gaussians purely based on what the camera literally sees, the AI will literally carve a deep hole right into the person's chest because the pixels in that specific region currently show a foreground arm. Lift4D has to logically deduce what happens to the object when it dips behind something else. When we look at the monocular scene depth map, you'll notice the person's arm is clearly mapped out as being physically closer to the camera. Next to it, we have the incredibly sharp, deduced scene occlusion mask that Lift4D generates. To generate this flawless mask, the system runs a strict element-wise logical comparison. It takes the overall estimated depth of the entire scene and it compares it directly, pixel by pixel, to the specific rendered depth of our 3D Gaussian object. If the scene's depth is closer to the camera than the object's depth, and it happens to fall within the object's tracking mask, the system immediately flags those specific pixels as occluded. This is brilliant. Lift4D knows, down to the exact mathematical pixel, what parts of the object are currently hidden in a blind spot.
So what does it do with that knowledge? Here is that full occlusion pipeline in action, visualizing the math we just discussed. You can see how equations 7 and 8 meticulously map this entire process out. Once the system isolates that high-contrast black and white occlusion mask, it faces a dilemma. It absolutely cannot use the raw video pixels to supervise the occluded part of the shirt, because again, those pixels literally show an arm. So instead, it uses the 3D geometry generated from Pillar 1 as a sort of color-corrected proxy. It runs a highly detailed per-channel histogram color matching process to ensure the lighting, shadows, and saturation of the proxy match the real, unoccluded video perfectly. Then it literally composites this color match proxy back into the actual video frame, but exactly and only where the occlusion mask dictates. This creates what the team calls a completed reference view. The AI is essentially digitally erasing the obstructing arm and seamlessly painting in a perfectly matched shirt. By doing this, it creates flawless training data for the canonical model, ensuring it never learns to carve a gaping, ugly hole into the 4D asset.
But wait, what about the actual back of the object? The camera literally never sees it at any point in the video. Here is the final piece of the appearance puzzle, guaranteeing that perfect visual style: image diffusion priors. Think of this process as hallucinating the unseen with an incredibly smart green screen. Lift4D utilizes a view-conditioned image diffusion prior. Specifically, they leverage a model called Stable 0123. The system randomly samples a completely novel, unseen viewing angle, renders a 2D image of the object from that angle, adds noise to it, and then denoises it. But it doesn't denoise it blindly. It denoises it conditioned specifically on that pristine, occlusion-free, completed reference view we just created in the last step. Because this diffusion prior is firmly anchored to a flawless, non-occluded reference image, it doesn't just hallucinate random, messy textures. It hallucinates highly realistic, context-aware textures that seamlessly and beautifully wrap around the unobserved back angles of the 3D object. It flawlessly completes the visual illusion, giving you a perfect 360-degree visual style.
Section 6, Results and Future Implications. It's time to prove the pipeline.
The theoretical math here is undeniably brilliant, but in AI research, we need hard data to see how it actually performs. The CMU team ran rigorous, exhaustive evaluations. They tested on the synthetic, consistent 4D benchmark dataset, as well as highly challenging, unconstrained, in-the-wild video datasets from Pexels and Davis that feature massive, unpredictable, non-rigid deformations. Let's really analyze this data table directly from the consistent 4D dataset. We are looking at three absolutely critical metrics for evaluating visual style and coherence. LPIPS measures perceptual distance, so a lower number is much better, because it means it closely matches reality. FVD is the Frechet video distance, measuring overall video realism and temporal coherence over time. Again, lower is better. And finally, the clip score measures semantic accuracy, so here, higher is better. When you look at the baselines, Banamo struggles immensely with these tasks. Newer models like Stag4D and the massive feed-forward model L4GM definitely show improvements, but look at the bottom row. Lift4D absolutely dominates across the entire board. Lift4D achieves an LPIPS of 0.116, the lowest perceptual distance by a wide margin, meaning its rendered visual style looks the closest to the true object. It absolutely crushes the FVD score at 592.44, proving vastly superior temporal stability without jitter, and it achieves the highest semantic accuracy with a clip score of 0.950. The raw data conclusively proves that fundamentally separating geometry priors from appearance priors creates a vastly superior, hyper-realistic 4D reconstruction.
And if you want to see what those numbers mean visually, this qualitative comparison is simply stunning. Look at the renderings from completely novel, unseen views. When we view the dog and the horse from an angle the original camera lens never captured, look at the catastrophic failures in models like L4GM, Stag4D, and Pad3R. They leave massive, jarring visual gaps. The horse's legs are literally detached and floating in space, the dog's body is completely distorted into a stretched, unnatural cylinder, and the geometry of the book is utterly fragmented. These baseline models fundamentally failed to bridge the computational gap between static priors and dynamic, moving sequences. Now look at the top row. Lift4D completes the geometry flawlessly. The horse has all four legs fully attached, physically grounded, and moving accurately in 3D space. The dog has a solid, cohesive, photorealistic body. By utilizing that sparse canonical model, enforcing the physical regularizations, and applying the carefully anchored diffusion prior, Lift4D infers a complete, temporally coherent, completely watertight 4D asset with a visual style that is practically indistinguishable from reality.
Now, to be fully impartial and truly understand this framework as researchers, we absolutely have to look at its limitations. Lift4D is incredible, but it is not without its assumptions and weaknesses. Because it operates as a cascaded, curriculum-based test-time optimization, its final output quality is inherently, permanently tied to the quality of those initial SAM 3D geometry predictions in Pillar 1. If Pillar 1 somehow produces highly corrupted, noisy geometry right out of the gate, this cascaded setup means those early errors can propagate all the way down the line without any overarching oversight, fundamentally limiting how good the final canonical model can be. Furthermore, the authors explicitly and transparently note in the paper that scenes featuring extremely complex, fine-grained interactions, for instance, a human hand intricately grasping, covering, and manipulating a very small object, remain highly difficult to track and reconstruct accurately. The rapid, severe micro-occlusions in a hand grasp still push the boundaries of what this occlusion masking can currently deduce.
To close out our explainer today, let's wrap up with a quick 30-second summary featuring your three most memorable takeaways. Number 1, Lift4D conclusively proves that a curriculum-based, category-agnostic optimization framework drastically outperforms older models that rely on rigid, narrow templates or scarce 4D training data. Number 2, passing notes across time via causal latent conditioning is the absolute key to preventing that jittery, inconsistent 3D geometry across video frames, stabilizing the whole visual style. And number 3, logically deducing exactly where occlusions happen allows advanced image diffusion models to hallucinate unseen textures flawlessly, without ever carving ugly holes into foreground objects. The true democratization of 4D capture is finally here. So I'll leave you with this provocative thought. If algorithms can now reconstruct true, manipulable 4D geometry directly from our casual, everyday smartphone videos, how will this transform the very future of gaming, digital art, and our entire media landscape? If you enjoyed this deep dive, please smash that like button and hit subscribe. You'll see the thumbs up and the notification bell right there on your screen, and be sure to check back tomorrow for another exciting paper deep dive on Gradient Daily.